Good afternoon, everyone. Thank you for attending today's webinar on the building science as it relates to residential buildings. This webinar will be recorded, and the recording is posted to the Colorado Energy Office's Code Adoption Toolkit. Usually takes at least a week, so please be patient. But if you have any questions, feel free to follow up with me on that. If there are issues with audio, write me in the chat. My name is Erica DeLello. I'm a project manager for Noresco, and this series is sponsored by the Colorado Energy Office with training materials created by BuildTank. So on here, I've got our webinar series. We've got Building Science 101 today. We did add a part 2 for the IRC for the 31st at noon as part of the webinar series, and you will be receiving more info on that, on how to register for it after this call. And then we've got 2 more lined up for next month, for February. We will also be adding additional trainings through June as well, so keep an eye out for more information on that. But there is also, of course, the opportunity, if you have a group that is interested in a specific topic or just wants a more personal experience where we go in person, or you have whatever the topic is, we can likely cover it as long as it relates to the IECC. And you can reach out to me if you'd like to set something up. I do want to highlight some of the resources that the Code Adoption Toolkit has on there. We've got a whole bunch of different things. It's always being updated, so keep an eye out for new releases as well. But the main thing I want to highlight today is the Colorado Codes Helpline, where the helpline is for anyone in Colorado to submit a question on any of the I codes or REACH codes. So for example, if you're a jurisdiction and need assistance on a plan review, or a homeowner or engineer with a question about code applicability, you can easily submit a question, and a subject matter expert will get back to you in just a few days' time. And you can access this helpline through the Code Adoption Toolkit as well. So all that to say, throughout the webinar, we want to encourage questions. So please use that Q&A function, and I'll let our presenter know at the end of the presentation. There's also the ability to raise your hand and ask a question at the end, so then I can unmute you. And then lastly, there will be a survey window that pops up following the webinar. If you could please take a minute to provide feedback so we can continue to improve on these webinars, that would be greatly appreciated. Today's presenter is Robbie Schwartz, and Robbie founded BuildTank to be a practical building think tank to do research, education, and work with builders to ensure that their homes not only comply with codes and programs, but also perform. At BuildTank, they strive to use what they learn from their fieldwork to affect meaningful change in the construction industry. He's also the new homes building advisor for Boulder County's Marshall Fire as well. So with that, Robbie, I'll pass it over to you to kick off our training here.
Great. Well, thank you so much, and for that introduction, and it flows well into our topic today, which is building science with regards to the residential energy code. And I'm going to turn off my video now so you can concentrate on the slides, but I'll come back on a little bit later here when we do Q&A. We have a lot of material to go through today. So we're going to talk about, obviously, the IECC and building science, the whole idea of control and predictability, the intent of the IECC, different compliance pathways quickly, but we're going to spend most of our time today on the different control layers in the house. Now, we have buildings, old buildings out there, from France to Taos, the Taos Pueblo here, that was, over 1,000 years old here. We have relatively newer buildings from the 1900s, or in this case, from the one on the left there is from 1765 here. And then we transitioned into wood-based construction in the early 18 or mid 1800s, I guess, or late 1800s here. And once we got to wood-based construction or wood frame construction, we see that things haven't changed that much in terms of the way that we're actually building or the materials that we're using for that. Yeah, we moved away from balloon framing to platform framing, but the big thing that's changed is the number of people that are touching our modern day houses. And that's one of the big reasons why we need to understand building science more and more. An NHB study that was done in 2020 showed that over 300 people are touching a modern day house today. And each of those people are really segmented into a specific category of what they're doing in that house. With one builder, we named that person a builder or a superintendent or a construction manager, who in theory understands how to take that house from foundation all the way through finished carpentry. So there's really not that difficult to understand why we have some problems with our houses, because we're not thinking about the totality of the house. We're thinking about just that little segment that we're doing in terms of trade people in that house. And we have generally one person, again, that construction manager is trying to understand the totality of the process here. So when we're looking at these older houses, we need to ask ourselves, why is this house a 100-year-old house? Why has the Taos Pueblo lasted for over 1,000 years? Often they're drafty, they're uncomfortable, yet they're incredibly durable. Their houses have lasted over time. And really the main reason for that, and the reason for our houses not performing as well as they did in the past from a durability perspective, is that our expectations of our houses have changed pretty dramatically, and that this house, this 100-year-old house, just because it's drafty and uncomfortable means that it can be incredibly durable because it has tremendous drying potential. Water is the thing that's going to destroy houses over time. So we really need to understand kind of the physics of water and the physics of how air and vapor and bulk water and energy in terms of heat flow through our houses move, so that we can gain control and predictability of the airflow, thermal flow, and moisture flow in our houses. In this house, again, it's so durable because it's so air leaky or so uncomfortable. It has the ability to dry if it gets wet. Now, these expectations are changing whole neighborhoods, whole cities. Older houses are being scraped, new houses are being built, but are we actually meeting people's expectations? And really, you see the genesis of the code development cycles time and time again changing because they are trying to achieve expectations that people have of our houses. And some simple expectations that we can think of, and with regards to those changes, so you take this 1910 house and you think about what comfort meant in 1910. Our notion of comfort was quite different. For example, people were willing to put on a sweater in the wintertime. They might have actually had to do some work in the winter to shovel some coal to heat that house. In the 2020s now, we really want to be able to walk around from room to room and floor to floor and be quote unquote comfortable. And we want to actually be able to do that in our underwear, let alone having to put on a sweater inside of our house to maintain comfort inside that house. Those expectations have fundamentally changed the way that we build our houses, and therefore we have to understand the building science so that we continue to have that long-term durability in our homes here. So some of the modern expectations, yeah, we still need that structural integrity. We want fire integrity. We want durable structures. We want healthy environments. We want that comfort. We want that efficiency. We want all these things. And how do we integrate all these expectations together in a house that can actually meet those expectations? So that's where we're trying to figure out how we are creating and providing control and predictability. And that's why we need to understand ultimately the control layers in our houses here. We understand ourselves as builders, and think of ourselves as builders in 1910 versus a builder today. So a builder in the early 1900s probably was a small family business where the people involved in the construction really took it from foundation through finished carpentry. And in today's world, builders really are guiding a process, and they've got these 300 trade partners that are touching our houses. So they really need to think of themselves as leaders of change and innovation to be able to build houses that meet our core expectations, our modern expectations, which means that they need to understand systems thinking and applied building science and how the code is trying to get us there. They need to understand how homes perform and how they don't perform and how we're going to, again, meet those expectations. They need to start the conversation early in the construction process about what people are expecting and how we're going to integrate that together with maybe an integrated design process, bringing in architects, engineers, specialists like energy raters or HVAC contractors or insulation specialists there to help educate our trade partners to understand how the science, the systems approach actually works to determine the objectives for a house. And then ultimately, every house is a process of evolution in terms of growing our understanding of how houses actually work. So we're going through this design, construction, testing, and evaluation process where we should be learning from that and taking it back to the design process. Right now, we're barely doing that, but we're not even taking what we're learning from a warranty process back into the design process very well and often. We can learn a lot from warranty to change the way that we design and construct so that we do better meet those expectations. But ultimately, what we're talking about is how do we understand the basic building science and how do we apply it in the field to get houses that actually perform? Because there's so much here that we need to integrate in together. And if we boil this down into a little bit less and talk about the fundamentals, we're talking about how air flows in our house, how heat flows in our house, and how moisture flows in our house, and how do we gain control and predictability of those things so that we get houses that are not only durable, those 100-year-old houses again, but houses that meet the core expectations of the people living in those houses. We've coined a term recently about high performance buildings. And this diagram here kind of talks about what we're trying to accomplish when we have a highly performing building, a building that is comfortable, healthy, durable, and efficient. And I think we can add the term resiliency as well in our modern world. You know, after the last fires that we've had here locally in Colorado, we want to be fire resilient. And then the power outage that happened in Texas, we want to be able to reside in our homes over time. So we're seeing severe weather events and other events happening due to climate change and whatnot that are making us think about resiliency as well in this puzzle of things. So systems thinking has been a kind of a key phrase for maybe, you know, since the industrial revolution in terms of factory lines and production lines here, but it's gained speed in housing as well within the last 30 or 40 years. And really the key term there when we think about systems thinking is not just the moving from the specific framer or insulator and thinking in this more holistic approach, but understanding this word synergy, where two or more things come together to achieve something that's greater than what they could achieve on their own. So again, the only way to meet these buyers' expectations, the people that are actually living in our houses, is to understand the synergy between insulation and air barriers, between ventilation and house tightness, between moisture management and long-term durability. All of these things come together, and the systematic approach helps us do that. So two or more things coming together. So we can think of it kind of in a simple way as insulation and an air barrier coming together to control heat flow, especially when you have fibrous insulation and you're trying to control the air pockets inside that fiber. But in the reality, when we bring insulation and air barriers together, we're getting more than just control of heat flow. We're also beginning to get more control of airflow in that house. And we're also getting more moisture flow control and predictability. And we're also getting better and improved indoor air quality. So just bringing those two things together, there's this synergistic relationship that is giving us 4 or 5 or 6 or other uh, uh, interactions there that are giving us these qualities, these and helping us meet those expectations that people have in their houses there. So when we start digging in a little bit more, there are kind of these 5 main parts to the system that we need to address and understand the synergies that are happening with these systems. We have the basic structure of the house. We have the systems, the mechanical systems, the HVAC, the plumbing, the lighting systems in our houses. We have the enclosure of that house to control moisture and heat and energy moving through that enclosure. And then we have the specific climate that house is in. And then we have this kind of wild card, the wild card being the people in that house. And we're going to take these different systems integrations here, and we're going to plop them into, again, that specific climate here. And that climate is defined by the IECC climate zone map here. And in Colorado, we're in dry climate zone B. You can see the dark line separating the dry climate zones from the moist climate zones. And in Colorado specifically, we have one of the largest variety of climate zones within our state here, from climate zone 4B to climate zone 7 and 8 up in Leadville and in our mountain areas as well. But the majority of Colorado on the front plains here anyway, the Front Range plains here are in climate zone 5B. And we just have to recognize that because the code does ask us to do things slightly different in climate zone B, the dry climate zone, versus 5A, the moist climate zone here. And so we need to understand the building science again and how we're going to apply that building science here on these homes as well here. So again, it comes ultimately down when we're talking about building science is gaining control of airflow, moisture flow, and thermal flow, and also gaining predictability. You know, I like to use McDonald's as a kind of a meme for predictability, because if I'm in Paris, France, or Los Angeles or Denver, Colorado here, and I go and I get a Big Mac, I know exactly what I'm going to get in any of those locations, and I know how I'm going to feel afterwards. So it's so predictable that that's what we want to translate into our homes, is gaining that control and that predictability throughout our houses. The predictable performance, predictable flow of energy, predictable vapor management, and all those things. So building science over the last 3 years has kind of consolidated all these concepts into understanding thermal flow, vapor flow, airflow, and bulk water management. Now, some people will put these in different order here, but I'm putting them in this order because that's kind of how they're addressed with regards to the energy code here. So we're going to look at these different layers here, but we're going to start with the intent of the IECC. And the intent statement of the IECC is important because if you break it into its 3 components, you can kind of see building science wrapped into them. So the first part of the intent statement says that the code shall regulate the design and construction of buildings for the effective use and conservation of energy over the useful life of the building. And it's really that blue section here that's getting us to understand that the code is trying to ensure that we have long-term durability in our houses there. Now, obviously, it's the energy code as well, so comfort is kind of implied, and energy efficiency and kind of cost of operation are kind of implied in the intent statement. So that's not specifically talked about there. The second part of the intent statement says that this code is intended to provide flexibility to permit innovative approaches and techniques to achieve this objective here. So the big part here is to provide flexibility. And I like to equate this to this statement from the Dalai Lama, where he says we need to learn the rules so that we know how to break them properly. And in that way, it's really telling me that we need to dive into the code book itself, the language in the code book itself, because it's giving us tons of options. It's not saying that we have to do things in one way, but it's saying that we need to do things in a variety of different ways to achieve one result. The result being a house that meets the intent of the code, that has a quantifiable amount of energy use in that house, if it's built to that specific code there. And we should have a quantifiable amount of performance in that house from a comfort perspective, a durability perspective, and so forth and so on there. And then the last intent statement says that the code is not intended to abridge safety, health, or environmental requirements contained in other applicable codes or ordinances, but we also need to realize the link between the IECC and health, safety, and durability in our houses there, from carbon monoxide poisonings and not backdrafting atmospherically appliances, and understanding the pressure balances in our houses, to understanding that health and safety also have to deal with controlling the building thermal envelope so that we can keep cool and warm and safe inside that house. We don't want to continue to have situations where people are living in their houses and they're actually dying inside their houses from either being too cold or too hot. And that is happening in our country right now, because we're not gaining that control and predictability of the building thermal envelope of that house there. So we want to maintain shelter. We want to maintain durability. We want to understand the cost that's associated with that. But we necessarily don't want to focus on first costs, because first costs take us away from understanding how all of these things integrate together to achieve what we're ultimately trying to achieve here. So the building science is primarily wrapped into Chapter 4 of the IECC, whether it's the 2021 or the 2015. Ultimately, the code is trying to gain predictability and control by building our houses tight, by having a sound building thermal envelope, and then by ventilating the house correctly in accordance to the code there. And if we do all those things, we get control and predictability of thermal flow, airflow, and moisture flow. Now, from my perspective, the IECC maybe concentrates a little bit too much on the building thermal envelope and not on other parts of the building assembly. So we always have to understand the relationship and the synergy that's gotten between the energy code and the IRC, the building code, as well, to ensure that we're getting a house that ultimately performs here. And so we'll talk a little bit about the IRC here and how these two codes, as a family of codes, work together to achieve our ultimate goals here. So the International Energy Conservation Codes have a number of requirements. And in the 2021 IECC, they got rid of this confusing word mandatory, and basically everything is just a requirement. So at its core, if you're not using the 2021 IECC, you have to look at prescriptive and mandatory requirements and understand that if there are installation requirements in the prescriptive section, those are also required regardless of the compliance pathway that you choose. And that's the realization that we came to in the 2021 IECC, is that there aren't prescriptive requirements and mandatory requirements. So they're just requirements for how you install things so that you get the synergies from the building science of these things that we're installing in our building thermal envelope to control thermal flow, in our vapor retarders to control vapor, water that's moving through our buildings, and so forth and so on here. Now, again, you have to fulfill those requirements regardless of the compliance pathways. And this is where the real flexibility is brought into the code from that intent statement. So we have these different compliance options in our codes here, and you don't really get the flexibility until you move to either the prescriptive UA compliance path, the total building performance, or the energy rating index pathways in conjunction with these additional energy efficiency packages, because these pathways provide us the ability to do a software energy model on the house. Now, you can do a very simple model using the prescriptive UA compliance, a ResCheck type model. Remember that ResCheck is the name of the software, not the name of the compliance option path there. Or you can do a more sophisticated energy model using the total building performance or the energy rating index pathway there. But the whole value of energy modeling is that you can fail fast and you can succeed even faster, meaning that I can demonstrate how the house is going to fail or not meet the intent of the code quickly, and I can get to a cost-effective way of meeting the requirements of the code in a very fast manner there that's going to speed the process, but also figure out how we're going to do it in the most cost-effective way. Now, what energy modeling does in its simplistic kind of terms is that it's a software that creates a reference home, which is the home that you're rating, and you compare the reference home to the home that you're actually rating. Now, the big thing about the reference home is that it's a geometric twin of the house that we're actually wanting to understand how it's going to perform. So we do a takeoff in the software, we enter the dimensions into the software of that house, and it creates two houses that are geometric twins of each other. One we call the rated home, which is the house that we're actually going to build. One we call the reference home, which is the fictional house, I guess, it created inside the software that we're going to compare the rated home to. Now, the reference home is defined by either the program or code that we're going to build to. So the IECC has a reference home that's defined by the R value table and the U value table, and we compare what we want to put into that house to the code reference home. And if we're better than or equal to that reference home in terms of performance, we're going to achieve that performance criteria. We're going to meet the intent of the code here. So kind of to explain that in a different way here, we have two houses inside the software that are geometric twins of each other. We have the builder's desired house compared to the reference home. And the reference home is created by the IECC prescriptive envelope U values and requirements that are in table R402.1.4. We then take the builders, whatever the builder specifications are for that house, and we input that into the software. And that way we have two houses that are geometrically the same, but they have different thermal envelope characteristics there. And now we can compare the builder's house to the reference home, and we can say that if the builder's house has better or equal to performance to the reference home, it's going to meet the intent of the code. And that's, in its simplicity, is what the energy modeling approaches, compliance approaches, allow us to do, because ultimately it allows us to do what we call a trade-off. And a trade-off says that if we're going to put something more in one assembly, then I can put something less in another assembly. So it increases the flexibility in terms of choosing how I'm going to put together my building thermal envelope, my building assemblies, the core wall assembly, the core roof assembly, foundation assembly. How am I going to do that in the most cost-effective way to get the level of performance that I'm trying to achieve? Whether that level of performance is the IECC or at a passive house level, they're going through an energy model to be able to figure out the best way to put those things together there. So in its simple terms, again, if I take the blue ball here and I say the blue ball is what I want to install. I want to install R38 attic insulation. But the energy code in the 2021 IECC says I have to install R60 there. And I say, heck, as a builder, I've never installed that much insulation in my attic, and I just purely don't want to do that. It means you have to move from the prescriptive approach to a performance approach to be able to do this trade-off. So if I'm going to put R38 in my attic, I'm putting less in my attic, therefore I have to do something more in other assemblies. And in this case, maybe I'm installing already better windows than the code complies. Maybe I'm building my houses tighter than the 3 air changes that the code requires. And maybe I've reduced duct leakage to the outdoors. And those 3 things, or maybe just one of those things, might be able to balance the equation so that I still have a house that meets the intent of the code, the energy performance of the code, uh, uh, in order to make that trade-off, that less insulation in the attic, and make it in the most, again, cost-effective way that we can make it there. So we need to think about those trade-offs and how those work, and then how we're going to get control of our building thermal envelope. So the building science here is that we need to understand how heat flows. Heat flows from a warm object to a cold object, or energy flows from a warm object to a cold object. And it can only do that if we understand what delta T is, and that's a temperature difference across the assembly. So we know which direction the energy is flowing. And the code tells us what our design temperatures have to be in the wintertime and in the summertime. So we know which way the energy is flowing in wintertime and in the summertime. And then it tells us we have to install insulation in our building thermal envelope, and insulation ultimately traps a pocket of air. And it's that stagnant pocket of air that ensures that we're going to be able to reduce that energy flow from higher concentrations to lower concentrations, which means that we have to have a thermal layer there, but we also have to have an air barrier here. So it works really the same way that we work with our clothes. So we have a fleece jacket that's trapping a pocket of air like a fiberglass bat. We have this Arc'teryx nylon shell over that. The nylon shell is the air barrier, just like the air barrier that we're going to install, so that we can get that stagnant pocket of air and reduce the flow of energy from higher concentrations to lower concentrations there. The other thing that we need to understand is that, again, the synergies of things here. Our HVAC system is designed before our house is built, and it's dependent on the specifications for that building thermal envelope there. And if we don't execute that building thermal envelope there, our design is not going to work. Yet we often don't go back and tweak the design to ensure that it matches better that building thermal envelope that we actually achieved there, especially when we don't achieve the R value. Maybe the bats have been installed poorly and we're not actually achieving an R20 in the wall assembly. Well, that might mean that we're going to need a slightly bigger HVAC system to make that work there. So we need to carry out the work so that we get the synergy from these assemblies working together here. So the IECC defines the building thermal envelopes specifically as an assembly of things that create a boundary condition between conditioned space and unconditioned space there. And then the code tells us that we have to depict that on our building thermal envelope so that it's not just the knowledge of the architect and potentially the builder, but the trade partners in the field understand where that boundary is happening and how we're going to ensure that we're going to get that separation between conditioned space and unconditioned space. And then what materials are we trying to do to reduce the heat or thermal flow through those assemblies here. So the function of the air barrier system is to enclose the insulation. That's our thermal envelope insulation, so that we get enclosed insulation cavities here that trap those pockets of air there. So we get air control, we get thermal control, and ultimately we get better moisture control in our assemblies. So it's crucial that we understand how the code defines the building thermal envelope and our air barrier systems here, because they're really using a belts and suspenders approach. When a lot of people think about air barriers as one plane in our building assembly, either it's on the outside with a weather-resistant barrier potentially, or it's on the inside with our drywall. The code is saying it's an assembly of things. So we're going to get that again, that synergy effect here, if we understand that our primary interior air barriers are drywall and our primary exterior air barrier is our exterior sheathing, and then they work together to control and gain control and predictability of airflow through our houses there. Now, if I choose to use a zip sheathing and I say that's my primary air barrier, it still doesn't negate the fact that the drywall and the continuity of the drywall on the inside is going to be a belt or suspenders approach, is going to help improve the overall air tightness and control and predictability that we're going to get in our houses there. So we want to understand these as approaches here. And the code, again, is telling us to depict that air barrier, that building thermal envelope, all the way around our houses. And in particular, we need to pay special attention where different assemblies are coming together. It's where the roof joins the wall, and the wall joins the floor system, and the floor system attaches to the foundation. Those are the key areas that we're really concerned about from an airflow and thermal flow perspective here. The code also defines the base R values and U values that we have to put into our building thermal envelope. And remember that they sometimes make mistakes when they print the code books. So you need to go to the errata to get the right R values and U values sometimes. And that's what happened in the 2021 IACC here. The code is also telling us to reduce thermal bridging in there, because the envelope isn't continuous in essence, where we have it's starting to ask us to put continuous insulation on the houses to reduce thermal bridging, because we have a tendency to design it rightly where we have one king stud, which is great, but the framer might decide, well, we need two king studs, because if one is good, two is better. And then if two is good, six is better. And if six is good, maybe 15 would be even better there. So we're just creating opportunities where we have less insulation, where we have more thermal bridging, where we have places where condensation is going to control there or gain an upper hand there. And we see that the code has requirements where we have to insulate our headers and our corners and whatnot and reduce the thermal bridging that's happening in our houses here. So also it means that we not only need to address the framing, but we need to address our cavities and how we're going to insulate those cavities. And we need to follow the manufactured instruction and the additional insulation and installation instructions that are embodied in the code there to ensure that we're going to get cavities that are insulated and insulated right. And if you look at this slide, you might be surprised that the number 2 cavity here has the highest R value, but it doesn't have the best performance at all there. So we want to make sure that things are installed properly, which gets us to kind of these fundamental questions that we should be asking us as we build our houses or inspected our houses is not only is the insulation there, but has it been installed so it actually works and functions in our houses there. Now we're going to move on to our vapor control layer here from our thermal control layer here. And we see that the vapor control layer is the component or components. So again, we're talking about these assembly of things that are designed and installed in assembly to control the movement of water into an assembly by the process of vapor diffusion here. So we're not talking about the movement of water into our assemblies that's being carried with air. And it turns out that the code kind of microscopically fixates on vapor control versus and using a vapor retarder to control that vapor retarder or that vapor movement into our assemblies versus the movement of water vapor into our assemblies by air. And so we need to not only think about the vapor retarder, but we need to think about the air barrier and potentially the water resistant barrier as well when we're thinking about water vapor transport. And the reason is that they've done a number of experiments over time here to determine that the flow of vapor directly through the pores of our drywall from higher concentrations in our climate zone. We're talking about climate zone 5 here, where we generally have higher moisture content inside our houses versus outside our houses. We see that it's a very slow transport mechanism, this notion of diffusion of water vapor through the pores of drywall from higher concentrations to lower concentrations, versus when we introduce 1 square inch of hole area, which is about the size of the net free area of a electrical outlet, we see that we get 30 quarts of water moving into that wall assembly over the course of a heating season versus a third of a quart of water moving through that same drywall from the process of diffusion. So what this tells me is that the building science has shown time and time again that we shouldn't necessarily concentrate on vapor retarders as much as house tightness to ensure that water vapor isn't getting into our assemblies through outlets and other holes in our building assemblies, and ultimately creating condensation points or problems inside of our assemblies here. Because if moisture in its water vapor state gets into that assembly and it ultimately touches a cold surface, it's going to condense. And it turns out that that cold surface doesn't have to be that cold. So if we have 35% relative humidity in our house at 70 degrees there, and we touch a surface that's at 40 degrees, we're going to get condensation inside that assembly. So anytime it's cold outside, like as cold as it is today outside, in the 20s maybe out there, we're going to get condensation. So we need to stop the water vapor or the bulk of the water vapor from getting into the assembly in the first place, which means we want an airtight assembly. And then we want to build assemblies that have forgiveness, that have drying potential, so that we don't trap that moisture in it. If it's going to diffuse into the assembly, we want it to have the ability to diffuse out of the assembly, which we call drying potential. So we want high permeability rather than low permeability in our assemblies. And you'll see that the IRC vapor management or vapor retarder sections in the R702.7 section of the IRC has changed pretty dramatically to allow more and more class 2 and 3 vapor retarders, which the class 3 vapor retarders basically latex paint on our houses there. So you'll need to go to that section of the IRC to understand the vapor retarders, because we simply don't have time today to do it. But the other part of it is blower door testing to confirm that our houses are airtight and that our assemblies are tighter, so that less vapor is moving into our assemblies with the air leakage that's happening in our houses there. So we need to move to air control here. And there are a variety of ways to control airflow, and the air barrier is the thing. So remember the belt and suspenders approach and our primary interior and exterior air barrier, and getting continuity of both those systems. So when I install that zip sheathing again on the outside, yeah, it might be my true primary air barrier on the outside, but I need to make sure that we have the continuity of not just that zip sheathing on the outside, but continuity of the drywall on the inside, to ensure that I have an assembly approach that's going to work as a belts and suspenders around our house. So continuity is a key air barrier attribute. Strength is a key air barrier attribute. That's why we don't want to necessarily rely on our poly that we've installed as a vapor retarder to also be our air barrier. Durability, how long is our air barrier going to last? Remember the intent statement of the code. We want those 50, 100-year-old houses. We don't want houses to fail in the first 5 to 10 years. I believe that air barriers that are stiff are much easier to install, and they work a lot better than any flexible type of air barrier there. However, I do admit that Passive House is showing that there are a new host of vapor retarder and air barrier materials that can be installed well that are flexible there. But again, it's all in the installation. And ultimately, when we talk about an air barrier, it has to be impermeable to airflow. So we're stopping the majority of that moisture that's going to get into our assemblies because of the impermeability of the air barrier rather than the permeability from a moisture perspective of our vapor retarders or our other assemblies here. So the code also defines continuous air barriers as a combination or assembly of things here. And the air barrier itself, one or more materials joined together. So again, continuity is a huge part of the air barrier assembly there. We want to make sure that it's working right. The code also tells us that we have to provide assembly details to ensure that these air barrier details are carried out in the field here. So air barrier details are dealing with how do we get the continuity in specific assemblies, like behind the air barrier behind the tub, or the air barrier in a drop ceiling, or the air barrier at an attic knee wall. How do we get those continuities? And all those things are described in the air barrier, air sealing, and insulation installation table in the code. So that name changed slightly in the 2021 IECC. The tables changed slightly in the 2021 IECC, but it's structured with the components down the right side, the air barrier details in the middle, and requirements in the middle column, and the insulation criteria and requirements in the right-hand column. These are requirements, and in the past, they were called mandatory requirements. In the 2021, they are just called requirements. You've got to do them. And it just ensures that your house is going to have no issue of meeting at least the 3 air change requirement in Climate Zone 5, if not better. And the better, the tighter, the better there. Again, that fundamental question, is it there and has it been installed so it actually works there? So we've got some air barriers installed behind the tub, but the continuity is lacking. It's not going to work. So we're going to test our assemblies with the blower door testing here to ensure that it's going to work. And we're getting better and better at sealing up these. The code is telling us to seal this assembly in these 3 locations here to make it work. But we've got to make sure that the house is airtight to not only withstand stack effect, wind effect, but also the mechanical pressure differences that we might be introducing into our houses here. So that means that we need to understand how air actually moves in our house. So we talked about how air is a freight train. It carries moisture, it carries pollutants, it carries energy from point A to point E. The problem is when it actually dumps its load inside of an assembly. That's when we're going to get condensation, because we have heat and moisture on a cold surface that creates condensation. So we need 2 things for air to actually move through our assemblies. We need a hole and we need a driving force. So if we think of this balloon, the rubber membrane of the balloon as our building thermal envelope, if I have an airtight building thermal envelope, there's pressure equalization on either side of the building thermal envelope. But if I untie this string and I create a hole, then I get unequal pressures and air can now move through the hole. So if I have a hole, but I don't have a pressure difference across the hole, air isn't going to move. Or if I have a surface that doesn't have a pressure difference across it and I have a hole, we're not going to get air to move across it. So air's a fluid, just like moisture or water's a fluid, but I need a hole and a driving force. And we can think of wind, we can think of stack effect, which is just air heating and rising is what describes stack effect. And we could think of pressure imbalances that are created by our HVAC systems as those driving forces for pressure differences across the assembly that are going to move air across the assembly. So if I build it tight and the wind still blows, I'm not going to get air moving through that hole. Air in equals air out. So a cubic foot of air into the house means a cubic foot of air is going to go out of the houses. So we ultimately, from an airflow perspective, need to ask, can our houses be too tight? And hopefully the idea of control and predictability is just being hammered into our brains now that we are going to answer no. it can't be too tight. And in fact, we're actually asking the wrong question. Our houses, we need to control airflow, so we're building tight. So the real question is, can our houses be underventilated? And the answer is yes. We need controlled whole house mechanical ventilation because we do need to bring air into our houses for the occupants, for background moisture control, but it's got to be in a controlled and predictable manner there. So that's why we build our houses as tight as we possibly can, and then we introduce a hole so that we can move air into our houses in a controlled and predictable manner. And it gets boiled down into this kind of building science mantra: build tight and ventilate right in there. So whole house control mechanical ventilation is required by the code. In the 2021 IRC, it's described a little bit differently. It's just basically saying you have to provide it regardless of how airtight the house is. And you can use supply, exhaust, or balanced ventilation strategies in order to make it happen there. Unfortunately, we do a whole session on controlled mechanical ventilation, and we don't have time to get into it in more depth there. So we're going to go into bulk water management here. So the ultimate objective of bulk water management is to use gravity to ensure that water that hits that house has the ability to drain down and then ultimately away from the foundation there. So we have this water control layer that we're required to put on our houses that's defined in the IRC as the water resistant barrier. It can be one layer of water resistant barrier, or it can be a couple layers, or again, it's that continuity there that we want to have. And it's described in the R703 section of the building code. The water resistant barrier in dry climates requirements is a little bit different than that in the moist climate zones. So especially when we're talking about stucco here, and when we talk about stucco, we actually are talking about needing two rain resistant barriers, or basically one that's going to be a sacrificial coat to the stucco and one that's actually going to be our water resistant barrier here. And the whole notion of the water resistant barrier comes because of our understanding that regardless of the cladding materials that we're going to put in our houses there, water's going to bypass it. So it doesn't matter if I'm using lap siding, I'm using brick, I'm using stucco, moisture is going to bypass those things. So we have to have the ability to drain that amount of moisture that bypasses our lap siding, for example, down our wall assembly and then ultimately away from our foundation with our grading or our foundation drains there. Which also means that because we can't rely 100% on our cladding materials, we have to be able to use belt and suspenders approach, which gets into these flashing details at windows and other penetrations through our assemblies that are described in the R703.4 section of the code. Again, flashing techniques of exterior windows and other areas are talked about in these assemblies. Now, it's not necessarily required unless you wanted to move to a different type of vapor management that gives us more forgiving drying assemblies, like a class 2 or 3 vapor retarder. But the biggest bang that we ultimately get is a vented rain screen on top of our water resistant barrier here. And if you do this, you're allowed to install just latex paint on top of your drywall in order to do the vapor retarder work, or that's going to stop vapor from moving into our assemblies by diffusion there, because we're allowing greater drying potential of these assemblies here. So different types of rain screens are required. And unfortunately in the IRC, they don't define the gap size that's needed. It turns out from a building science investigation perspective, we only need about 3/16 or 3/8 of a gap, roughly in that range there. So these types of materials are providing enough enough gap so that moisture in its bulk stage can drain down there. It's not going to get enough hydroscopic pressure there to hold it in place. It's going to be able to drain freely down behind the siding there. Again, siding is not going to protect our assemblies completely. It does protect them to some extent, but water will bypass our siding materials here. Therefore, we need these layers of water resistant barriers to drain behind here. And in these two cases, we've got the sacrificial coat with the tar paper on top of the drain wrap, in this case, the Tyvek brand drain wrap, or if we have stucco on it, that 2 layers of WRB, the layer that's adjacent to the stucco actually is a sacrificial coat there in our assemblies there. So ultimately, when we're talking about water and bulk water management for our homes, we're talking about this hygrothermal balance, where ultimately wetting mechanisms are equal to drying mechanisms, so that we have this balanced equation here, so that we're not trapping moisture and driving it into our assemblies. We're allowing it to evaporate or dry or drain down and out. So in order to ultimately gain these building science principles and integrate them into our houses, we really need to think about integrated design processes. Integrated design processes help us further define the project, not only from the IECC or energy performance perspective and how we're going to get control and predictability, but also from our long-term durability perspective, from the cost of ownership perspective. All of these things can be defined into it. And these building science principles that are kind of associated into the codes through understanding the control layers that we're building into our houses helps us in this integrated design process and integrating it into the codes there as well. So we're able to share responsibilities by bringing the right team together. It's not only the architect's job, but if we bring the architect, the builder, trade partners, energy professionals together, we can get a system that's going to work. And you can ultimately create building systems that are repeatable. And yeah, you put a different cladding on that house, but the base core building thermal envelope is the same from house to house to house because it performs, it works there. View things holistically instead of one at a time. Information sharing and research, integration of our structure, our systems, our enclosure, our climates, our occupants, all those things need to be think about. So to conclude here, we ran through a lot of material there, but applied building science involves that systematic approach. Our ultimate gain is gaining control and predictability of airflow, moisture flow, and thermal flow in our houses. How do we do that? We understand the science of how we are creating bulk water management, air control in our houses, vapor control in our houses, and ultimately thermal control in our houses. Again, the code kind of looks at it in the opposite direction, but the thing that destroys houses from a building science perspective is moisture. So bulk water is key, is the first one there. Air control, because air carries moisture and pollutants, is second. Vapor control is third from a building science perspective, because again, it's dealing with moisture. And then fourth on our list from a building science perspective is the thermal control there. But again, we're integrating these things with customers' expectations, and thermal control is key to a customer's expectations. So ultimately, it goes back to the systems approach and the idea of synergy, where 2 or more things are coming together to achieve things that we couldn't achieve before, like that comfort expectation that client might have there. So the integrated design process is key. Design and build for comfort, durability, efficiency, and now resiliency as well there. So again, we went through a ton there. Anytime you get an opportunity to do a building science kind of introduction, it's worthwhile. So I invite you to listen to this again, because it's taped and is going to be posted, as Erica said. And then if you have any questions, don't hesitate to reach out or ask them now.
Thanks so much, Robbie. That was a great presentation, as always. I'll open it up for questions. Feel free to raise your hand or put your questions in the chat. And I'm going to stop the recording now.